So let us turn now to the mysterious notation we have been using for functions with multiple inputs. So what we have been seeing is that when we have a function which takes two inputs like plus, instead of using the familiar notation where we use a bracket and we put the arguments inside the bracket separated by commas, instead we just write the arguments one after the other separated by spaces. Now when we write a function like plus in the usual way, we indicate that it takes two arguments, and this is called its arity, right? So the arity of a function is how many arguments it takes. So in this case we say that plus is a binary function. So you have binary functions, unary functions take only one argument, and so on. So this becomes part of the definition of the function, and when we use the function we have to ensure that we supply the right number of arguments. So this is the conventional point of view. Now a radical departure from this is to assume that all functions take only one input, and this is the principle behind the notation that we have been using, and we will see in a minute how it works. Now just as a piece of terminology, this style of writing functions where every function is a function of only one argument is called currying. So it has nothing to do with cooking, but rather it is named after the logician Haskell Curry, who made it popular. So Haskell Curry is not in fact the person who invented it. The person who invented it was another logician called Schoenfinkel. But Haskell Curry was the logician who made this style of notation for functions popular. And another piece of interest for us is that the language Haskell, you might have wondered where the name Haskell came from. Well, Haskell is actually named after the logician Haskell Curry. So let's look at these two viewpoints of functions. So on the left, we have our familiar plus, which takes two arguments n and m and produces as output the answer n plus m. On the right is a picture of how we are supposed to think about the curried version. Right? So what we are saying now is that plus, as we have defined it, takes only one argument. So the one argument it takes is the first argument. So effectively, we start by consuming this n, right? So plus consumes this n, so that is this box, and it produces a new function in which n has now been absorbed. So now we have a function which will add n to whatever it gets. Okay? So that's the principle. So you, instead of consuming multiple arguments in one shot, you consume one argument at a time, and then you transform yourself into a new function in which part of the functionality is internalized. So plus has consumed the first argument and become a fixed function called plus n, which will add n to whatever. So if the first argument was 2, then now this new function will be called plus 2. It will add 2 to whatever it gets. And now this new function, which is now going to consume the m, okay, is now going to take this m, add n to it, which has already been built in, and give us n plus m. So the idea in currying is that you, instead of multiple arguments, you get a sequence of functions. Right? So you consume one argument at a time. Each argument transforms the function in some way by internalizing the most recent argument and creating a new function which will consume one more argument, and so on. So let's try to look at the type of the new plus that we have defined. So if we start from the end, okay, the last thing that happens is a function plus n, which takes an int as input and produces an int as output. So this particular function here is int to int. Okay? And this whole thing is the output of plus. So therefore, the type of plus is something that consumes an int and produces this function. So that's why we get that the type of plus is from an input int, okay, to an output into it. So this output into int is this box, and the input int is the original int, right? So working backwards, we can take a curried function and work from the last box backwards to construct its type like this. Let's look at another example, one that takes maybe 3 inputs. So supposing we have a plus 3, which will add 3 numbers, right? So now again in the same way, when I first consume the first n, okay, I will get something which internalizes the n. So now it will add n to whatever it's going to get as the next input. Now we are not done, so we will now consume one more input, which is this one, and we will now have something which adds n plus m to whatever it gets. And finally, when we consume the third input here, okay, we will have this function which takes us from a number p to the number n plus m plus p. And the point is that this n plus m is kind of built into the function. Right? It has already been hardwired in a sense because we have consumed n and m as previous inputs. So now again working backwards, right? So this last thing is this last box here. So this is an int to int function. So that is this type. So therefore, if I go to the previous box, right? So this now takes as input an int and produces that. So that is this function. And finally, the outermost takes an int and produces int2 into int, and therefore the type of plus 3 is this whole expression. So if we have a curried function, we consume the inputs one at a time. Each input transforms the function into one where one value is frozen in some sense. So the function now becomes one where one argument is fixed. Right? So we keep consuming one argument at a time, keep transforming the function so that it now has some values fixed into it. And we can recover the type of the function by working backwards from the last box to the first box. So in general, we could have a function which takes, say, n arguments and produces an answer. So suppose in this particular function that we are looking at, each of these inputs 1 to n is int, and say the last one is of type bool. Then by our earlier description, we would start by working backwards. So the last box would take the last input xn and produce y. So this would be int to bool. Right? So this is this last thing, and then the previous box would have taken xn minus 1 and produce this function that will be int to into bool and so on. So we'll get this nested thing sequence of int to int to int to it finally with an int to bool. And logically, if we look at the expression, the original function f first consumes x1 and it becomes a new function. So this is our second box, right? So this is like an f prime or an f1. f1 consumes x2 and this becomes a new function which has x1 and x2 into it, we call f2. So we have this implicit bracketing of the types in one sense where the innermost bracket corresponds to the rightmost function, the last input and the last output. And we have the corresponding bracketing of the way the function is used, which is that we first consume x1, then we consume x2 and so on. Now fortunately, Haskell knows this. Right? So there is an implicit bracketing which Haskell uses depending on the type of expression that we use. We are familiar with implicit bracketing for arithmetic. For example, we have this BODMAS, right? So we have in BODMAS, it says that if I write, for instance, 7 plus 2 times 3, then it is not going to be 9 times 3. This is not the correct answer, right? So this is not 9 times 3, rather it is 7 plus 6, right? So there is a precedence which says that it is bracketed like this. Okay, so that says division and multiplication are bound tighter than addition and subtraction. Now in a similar way, when it sees expressions like these arrows, then Haskell knows that it must bracket them in a particular way, and in particular it will bracket this starting from the right. So it will first put a bracket around int to bool, then around the previous one and so on. So it will produce from the upper expression without any brackets the lower expression, and we can freely use the upper expression without worrying about all these messy nested brackets. In the same way, when we write a function with arguments as a call to the function, it will implicitly assume that the function is bracketed from the left. So it will put in these brackets. It will start with a bracket around x1, then a bracket around x2 and so on. And finally it will produce this bracket around this. So we don't have to worry about these brackets. So that's very nice for us. So it means that the built-in bracketing rules in Haskell take care of the usual thing that we expect. So unless we want to do something unusual, we don't need brackets. Now, we have seen an example where this can create problems. Remember, when we defined factorial, we had to be careful to put a bracket around the n minus 1. And that is precisely because of this rule, because Haskell, when it sees factorial of n minus 1 without brackets, will first take factorial and bind it to the nearest thing. And this is like having two different operators. One is factorial with an argument and the other is subtraction. So just like division and multiplication will get bound ahead of subtraction, so will the function call. So this becomes factorial of n minus 1, and this is not what we expect. So we have to be a little aware of how this bracketing is done, because in such situations we may need to insert brackets to ensure that Haskell is understanding the expression the way we intend it. So to summarize, Haskell uses currying as a notation for functions. And in currying, the basic simplification is that functions don't have arities. We don't have to say a function is a binary function or a k-ary function taking k arguments. Every function takes only one argument. So if a function takes multiple arguments, it consumes these one after the other. Each argument transforms the function by internalizing that argument and making it into a new function where one of the arguments is frozen. So this becomes very convenient. We will also see that we can use these intermediate functions in other contexts. So there is actually, if we define a function of two arguments, then a function in which only one argument is provided in currying is partially another function, right? It says if I take plus mn and I feed 7, then plus 7 is a new function which will add 7 to whatever it gets. I can actually treat this partially instantiated function as a real function in many contexts, as we will see. And associated with currying is this implicit bracketing, which is right to left for types and left to right for function application. But fortunately, this bracketing is built into Haskell's bracketing rules along with arithmetic and Boolean expressions. So we don't have to use brackets unless we really want to disambiguate something.